Right. Now, I'm just going to start off with the page number 2. Okay, so can everyone flip to page number 2? Now, let's do some recap on the previous chapters that we have learned in secondary 3. Now, in secondary 3, what have we learned? Okay, I assume that most of you are secondary 3 students going to secondary 4 next year. Now, you realize that in secondary 3, we learned a very different topic. So we learned, for example, we started with elements compound mixture. We move on to atomic structure, learn about chemical bonding, moving on to acid and bases, as well as other topics such as metals. Some schools may have taught metals, okay, and periodic table as well. Now, all these chapters, you have learned many things, okay? And one thing that I like students to do, right, is they can actually try to write out a consolidated version of their notes. So if I have a piece of paper with me, I can actually write down what I remember from the notes itself, and I can actually fill in, okay, the content gaps that I have. Once I'm done with the notes, I can go and take a look at my school notes or my textbook and try and fill in the content gaps. Okay, and this way you will ensure that you do not have any content gaps in your studying, and you will ensure that all the questions that you have adequately covered the necessary content or concepts required to do those questions. Okay, so let's start off with the first part, which is an introduction to redox reactions. Now, for redox reactions, right, this is a chapter that some students find it very new and very unknown to them. I'm going to simplify it very easily for you, okay, so that you will not think that this chapter is very difficult and this chapter will become like a piece of cake. Let's look at this together. Now, let's learn what is the meaning of redox reactions, okay? Now, most reactions that we learned before involve both the oxidation and reduction processes. Now, these two words are a bit new to you, okay? But we'll explore them individually. Now, how does the term redox actually come about? It is basically where there is a simultaneous reduction and oxidation taking place. Okay, so I have reduction and I have oxidation taking place at the same time. Now, reduction and oxidation are something that is a little bit strange to us or unfamiliar to us, but it's okay, let's learn it together, right? So let's fill in the first box over here. A redox reaction is where an oxidation and reduction actually takes place simultaneously. Okay, so it turns out some reactions can be classified as an oxidation reaction, and some reactions can actually be classified as a reduction reaction. And let's learn the method to actually help us to deduce what kind of reaction is one reaction, okay? So let's skip the shoe method. I'm going to teach it to you later. Let's go down to page number 3. Now, in page 3, okay, I will show you the criteria for us to actually tell us whether something is an oxidation reaction or a reduction reaction. Now, very simply, right, some time ago, scientists have actually found out that some reactions, they gain oxygen. Some reactions require oxygen, right? I supply oxygen in, for example, burning, a combustion, okay, we require oxygen, right? And some reaction, right, they actually lose oxygen. For example, if I heat a metal, okay, I can reduce it to the metal, heat a metal oxide, I can reduce it to the metal itself. And some of these reactions, right, they involve this thing known as oxidation and reduction. So scientists have come up with this plan to define for us what is the term oxidation and what is the term reduction referring to. Now, oxidation is referred to the gain in oxygen, whilst reduction is referred to as the loss of oxygen. Now, if you don't understand this, don't worry, let's proceed on first. Now, oxidation and reduction is simply referring to some species in a reaction undergoing a certain type of change. Okay, whether or not they gain oxygen, then I call this oxidized. And if I lose oxygen, originally I'm bonded to oxygen, and I lose the oxygen away, then I would say that it is a reduction reaction, or I have been reduced. So I see over here, let's consolidate our learning so far. When a substance gains oxygen atom in a reaction, we say that it has been oxidized. Okay, on the other hand, if a substance loses oxygen atoms in a reaction, we say that it is reduced. Can so far? So when it gains oxygen, we say that it is getting oxidized. And when it's losing oxygen, we say that it is reduced. So I'm going to give you a very simple analogy over here. Okay, let's find an empty space at the top over here. Let's write this down together. Now, if I have element A, right, okay, and I react this together with oxygen. Now, after the reaction, I actually get this thing over here called AO2, where the A is actually bonded to the oxygen. Okay, and this over here, when A gains the oxygen itself, this reaction over here is known as an oxidation reaction. And how do we represent oxidation reaction? We will put a square bracket right at O and close the square bracket. Can? Now, if I tell you that I have another reaction, if I have, for example, 2XO, okay, this is my my reactants. After the reaction, I actually get 2X plus O2. Now, the X originally is bonded to the oxygen, but after the reaction, the X is now standalone away from the oxygen atom. This reaction over here means that it has lost the oxygen, right? So just now I have oxygen, now I don't have oxygen anymore. I'm referring to X, just now X got oxygen, now X don't have oxygen anymore. This is known as a reduction reaction. Okay, so how do you write down reduction? Square bracket R. Okay, so if you look at this one over here, it may seem confusing to some of you because what is A, what is X? Don't worry. Let's look at the first example to illustrate our ideas. Now, let's look at example 1. In example 1, we look at how aluminum, when it's burning in oxygen, we form aluminum oxide, right? So the equation looks something like this. Now, let's look at the equation. Let's spend half a minute looking at the equation itself. Okay. Now, in this equation itself, you will realize some things. You'll realize that there is this thing over here, which are the mole ratios between the reactants. Okay, so once in secondary 3, we learned about mole concept, right? So these are our mole ratios or the stoichiometric ratios between each of the reactants. But in redox reaction, okay, the good thing is, okay, write this down. In redox reactions, okay, you do not need to care about the mole ratios. Okay, so you do not need to care, or you just can disregard the mole ratios. Okay, so when we look at an equation like this, I will just pretend that all these numbers are not there for simplicity. Okay, so when I look at an equation that is given to us, we do not need to bother about the molar ratios. We only need to bother about the things that I've just highlighted in blue, yellow, and red. Now, in redox reactions, it's important for us to actually classify what is the reactant and what is the product. Okay, now reactant is very simple. Reactant is on the left-hand side of the arrow, which are the things that you put in for the reaction to take place. On the other hand, the product is what is produced after the reaction, which is the one that's right-hand side of the arrow. So always you must be very clear where the arrow is, and you must make sure that you do not confuse it together. Okay. Now, in this case over here, let's look at this reaction. You will see that aluminum is reacting with oxygen to form Al2O3. Aluminum is reacting with oxygen to form Al2O3, aluminum oxide. And in this case, what can we say? Before this previously, okay, we understand that the term oxidation refers to the gain in oxygen, and the term reduction refers to the loss of oxygen. So you see, aluminum originally don't have oxygen to itself, don't have oxygen bonded to itself. After the reaction, it grabs onto some O and it forms Al2O3. And this reaction is termed as an oxidation reaction. Okay, so the species, okay, the species that have gotten the oxygen, we will call it to be oxidized. Okay, so this is the first criteria, which is using oxygen, okay, to help us deduce what is getting oxidized and what is getting reduced. Give you some time to copy this down. If you have any questions at any point of time, once again, for those who have just joined, you can just type it into the Zoom chat or at any point of time, or you can just unmute yourself, okay, and ask the questions as well. Okay. Let's move on now to question number 2. Now, question number 2, I want you to try out this question. Okay. Now, okay, let's try out question number 2. We are asked to find out whether or not this reaction over here is a redox reaction. So let's read out the question. Magnesium is heated with copper 2 oxide. The reaction is as follows. So this equation is given to you where we can see that magnesium is heated with copper 2 oxide, which will give us magnesium oxide and copper. Okay, I want you to spend 30 seconds and think whether or not this is a redox reaction. Okay, so once you're done with whether or not it is a redox reaction, once you have your answer, you can type it in the chat whether it is a yes or is it a no. Hey, remember what is the criteria for a redox reaction? When we gain oxygen, we call it undergoing oxidation. And when it's losing oxygen, it is considered a reduction reaction. So can anyone text into the chat, please? Is this a redox reaction? Okay, yes, I see. Mara says it is a redox reaction. Okay, does anyone agree? Okay, very good. Thank you, Natalie. Okay, so yes, I think we have our answer. Yes, this is a redox reaction. Okay, so yes, this is a redox reaction. Now, I want to show you, right, why this is a redox reaction in a very, very systematic manner. Okay, now students, please don't go around saying, oh, this something get oxidized, something get reduced. You don't really know what is happening, right? But what is the foolproof method that you can ensure that you know how to identify a redox reaction? Follow me closely now. Now, I want you to first be able to identify the species in the reaction. Okay, so first step is to identify the species in the reaction. We have first magnesium, we have copper, we have oxygen. Now, let me use the same color coding to do this on the right-hand side. Okay, let's look closely. Yeah, let's look at magnesium first. I need to make sure that the arrow, I know where the arrow is, okay? So please make sure that you color the arrow out or make sure that you take note of where the arrow is. Now, let's look at magnesium first. On the left-hand side of magnesium, of the reaction of the arrow, there is no oxygen. However, after the reaction, what happens? Magnesium is now bonded to oxygen, right? Can you see here? Magnesium is now bonded to oxygen. And what is this reaction known as? This is called an oxidation reaction, right? Because magnesium originally no oxygen. After the reaction, now got oxygen. This is an oxidation reaction. What about copper oxide? Let's look at copper oxide here. Now, copper oxide, after the reaction, is now just Cu only. Now just Cu only, right? So let's deal with the yellow one first. Yellow was originally bonded to oxygen. Now it is just stand alone. There is no more oxygen. This is a loss of oxygen, and we will term this as a reduction reaction. Is this okay, everybody? So oxidation reaction and reduction reaction. Therefore, if these two criteria are fulfilled, where there is an oxidation reaction and a reduction reaction, then we will call this a redox reaction. Okay, so let's write this down in the answer key over here, answer space over here. So yes, because magnesium is oxidized from Mg to MgO. Okay, This is a gain of oxygen, whilst, okay, copper is reduced from copper oxide, CuO, to copper metal itself. This is known as a loss of oxygen. Okay. So key point is you must tell me what is oxidized because it gains oxygen, whilst what is reduced because it loses oxygen. Is everyone okay with this? Can I? Okay. If you're all good with this, let's go down to the next page on page number 4. Okay, I'll leave this here for those of you who still need to copy the answer. The rest of us can go down to page number 4. Okay, in the next page, okay, we look at concept number 3. Now, concept number 3 tells us what is oxidation and reduction in terms of gain or loss of hydrogen. Okay, gain or loss of hydrogen. Just now we talk about oxygen, right? Now we talk about hydrogen. Okay, now for hydrogen itself, how are we able to determine something whether or not is it oxidized or is it reduced? I'm going to use the same framework as just now to illustrate this idea. Now, if I have element A, I react it with hydrogen. After the reaction, I get AH2. Okay, I will term this a reduction reaction. On the other hand, if I have, for example, XH, which reacts to become X and H2, this over here is an oxidation reaction. Okay, this is what I need to tell you at the first moment. Okay, now, therefore, this brings us to the key idea that oxidation is the loss of hydrogen, whilst reduction is the gain of hydrogen atoms. Is that okay? Now, therefore, when a substance gains hydrogen atom in a reaction, it is said to be reduced. Whilst if a substance loses hydrogen atoms in a reaction, it is said to be oxidized. So you can see over here that oxidation is the loss of hydrogen, okay, and reduction is the gain of hydrogen. It is the opposite of oxygen. Okay, if you're all good with this, let's look at example 3 to illustrate what we mean by this. Okay, in example 3, we see how bromine is reacted with hydrogen sulfide in the following reaction. So we have bromine over here. Okay, so sorry, I'm going to use color coding again. Okay, hydrogen, I have sulfur. Then I have bromine, I have hydrogen, I have sulfur. Now, back to this color coding over here. Now, we are asked to identify the species undergoing oxidation and reduction and explain it with regards to gain or loss of hydrogen. Let's look at the figure itself. Okay, let's look at the equation first. Now, before the reaction, okay, always notice where is the arrow? Where is the arrow? Okay, you will notice that there is bromine, there is H2, and there is sulfur. So let's look at bromine first. Now, bromine on the left-hand side to the right-hand side, what has happened? There is a gain of oxygen, gain of hydrogen, right? Now, gain of hydrogen, what do we say it is? It is a reduction reaction, right? What about this reaction over here to form sulfur? Before this sulfur was bonded to hydrogen, after the reaction, sulfur has no more hydrogen. We will term this, okay, as an oxidation reaction. Okay? Now, so you must tell me what are the species undergoing oxidation and reduction. Okay, we see that Br is oxidized. So sorry, Br is reduced. Okay. Now you must be very careful when you are doing the answering. Is that you must tell me what is the element instead of telling me what is the compound. Okay, you must tell me the element. Br2, Br is reduced, but the compound is Br2. Okay, so you must tell me bromine, the element, is reduced. Okay, from Br2 to HBr, since it has gained hydrogen atoms. Okay. Now, then you must also tell me what is getting oxidized. Okay, oxidized is sulfur, right? So you cannot tell me H2S is oxidized because whatever that is left on the right hand side is only sulfur, right? So you tell me that sulfur is oxidized. Okay, from what? From H2S to sulfur itself. This is a loss of hydrogen atoms. Is that okay, everyone? Okay, so you answer the question by telling me what is undergoing oxidation and reduction and explain to it with the gain or loss of hydrogen. Okay, let's now go on to the next part, which is on ionic half equation. So if you're done with this, can you give me a thumbs up? Okay, thank you. Let's go down to ionic half equation, shall we? Now, ionic half equation is an idea that I want to re-emphasize again, because this one over here is quite important. Okay, so let's look back at page number 3, right? Let's look at this equation over here very specifically. Now I'm gonna I'm gonna copy this equation, okay, and bring it down into the next part over here. Okay, the ionic half equations over here. I'm gonna use this equation to illustrate something to you. Now, what is the term ionic half equation supposed to mean? Let's unpack this term by term. Now, some students they rush into doing redox reactions chapter and they really don't understand what is meant by ionic half equations. So, what is ionic half equation? Ionic simply means there must be ions in the equation, right? So I must have ions present in the equation. Now, half equation, on the other hand, refers to whether is it an oxidation reaction or is it a reduction reaction, okay? So you see redox reaction is together. I break it into reduction and oxidation, okay? So a reduction reaction or oxidation reaction, okay? And there is also, okay, something that you want to take note, which is since there must be ions present, there must always be electrons as well. Okay, electrons as well. Electrons as well. Just now, what did we say about this reaction over here? Let's look at this reaction again. Magnesium is undergoing what? Oxidation, right? And this is undergoing reduction. Okay, so everyone can copy this equation down onto your paper. Now, let me tell you how to write the ionic half equation. Okay, first step to writing an ionic half equation always is to identify the ions. Okay, let's identify the ions in both the reactants and the products. Now, how do I do this? Very simply, let's look at stuff that are ionic in the reaction. Now, can you tell me over here, okay, I give you an option, 1 or 2, which one, magnesium or CuO, is ionic? Can you comment into the chat box? Okay, very good. Mara says 2. Okay, anyone has any answers? Anyone disagrees or agrees? Okay, Rose says 2. Okay, Kenneth says 2. Anyone else? Natalie, any idea? Jasmine, Doreen, and Amanda, any idea? Okay, 2 as well. Okay, very good. So you have correctly identified that copper oxide is an ionic molecule or ionic compound, right? So you can see over here that it's made of copper 2 plus ion and O2 minus ion. Similarly, on the right-hand side, I can apply the same idea to magnesium oxide to expose the ions, which is Mg2 plus and O2 minus. Now, I want you to look at this very carefully, okay? So let's look at magnesium first, okay? I'm going to highlight magnesium again. Now, let's write out the equation, okay? Write down the equation. Now, from magnesium, at the left-hand side of the reaction, I'm not going to be bothered about the copper oxide, okay? So this is a half equation. For magnesium, I look at magnesium by itself. Copper, I look at copper by itself, okay? I don't mix up the two. So magnesium 2, magnesium 2 plus. This is the half equation, okay? So it goes from magnesium to magnesium 2 plus. Now, this process over here, what happens? The charge is not balanced. Here is magnesium 0, but here is 2 plus. So what has actually happened? Now, in order for me to become positive in nature, what is the process that is involved? Okay, is it the gain of proton or is it the loss of electron? Okay, you have learned in chemical bonding that it's impossible for you to gain proton. Okay, you have learned in atomic structure as well. It's impossible for you to gain proton. And that's the reason why this process for Mg to Mg2 plus involve a loss of electron. Okay, so I put a plus here. Why is that so? Because originally there was electron. Now I kick away the electron. So the electron has exited the magnesium, right? So if I have 2 plus here, I must have 2 electrons to balance out because electron is negative. Okay, so this over here is what we call the ionic half equation. This is the first one. There are 2 ionic half equations here. Okay, maybe I'll label it as A and B. Okay, okay, this is equation A. Now, what is important in ionic half equation is not so much about whether or not your species have 2 plus, 1 plus, 0 plus, but rather it is the state symbol, okay? It is a state symbol that's very important. Now, what is the state symbol? The state symbol basically, is it solid, is it aqueous, or is it liquid? It's very important in this chapter because different type of reaction will involve different type of state symbols. And therefore, it's important for you to label in that this is a solid to solid reaction. Some reaction may be solid to aqueous, some reaction will be solid to gaseous, and liquid to gaseous as well. Okay, electron do not have state symbol because electron is a very negligible particle, subatomic particle. Okay, so we have settled magnesium already. Next one we deal with is copper. Right, next one we deal with is copper, right? So let's look at B. Now, copper is, okay, from here, we know that it's copper 2 plus. Okay, I'm going to highlight this, color code this again. Copper 2 plus to copper itself. Okay, I'm going to write this down. Cu2 plus to Cu itself. Now, what does this reaction involve? Okay, what does this reaction involve? Originally, it is positive. Now it has 0 charge. Of course, it must involve the gain of electron, right? Gain of electron. Therefore, I must add 2 electrons to this particular species for me to get copper. Okay? So the copper ion, the copper 2 ion, you must gain 2 electrons before you can become copper. Now, why am I telling you this? Now, it's because, right, you must understand the fundamental of redox reactions before you can proceed on to learn what is the criteria required. So there are 4 criteria for redox reactions, and we're going to explore the other 2 later. So we have explored oxygen first and hydrogen already, right? So next 2 will be coming up shortly, okay? But before that, let's do this first. Now, I want to teach you something over here. Why is it that some student may ask, why is it that oxygen appear on the left-hand side and the right-hand side, but I don't bother about it? Why I don't care about it? Do you realize that this oxygen over here is actually an oxide ion, which is O2 minus, both on the left-hand side of the equation and on the right-hand side of the equation. This means that it has not changed from the left to the right of the equation, from the start to the end of the equation as well. Okay, no chemical change. Therefore, oxygen is left outside of the equation. And this is what we call a spectator ion as well. Okay, so I say again, oxygen remains unchanged from left to right. It's called a spectator ion. So let's look at A and B. A and B has special names, okay? Now, we look at this carefully. Mg to Mg2 plus, just now I ascertained that this reaction, what is it? It is the oxidation reaction, right? So I will term this as the oxidation equation. And the reaction below, we see that copper from here to here is a reduction reaction. So therefore, this is a reduction reaction or reduction equation. Okay, so give us some time to copy this down and digest this first before we move on to the next part. Okay, so from this equation, I want to teach you something as well. You can see over here that we have electron. Now, the position of electron is very important. Whether is it on the left-hand side of the equation or the right-hand side of the equation, they are very important. Now, why is this so? Okay, I'm going to just highlight the equation for you first. I'm going to just highlight the electron for you first, okay, before we start explaining deeper of what this means. Now, in the top equation, right, okay, we see that there is oxidation reaction. Now, an oxidation reaction is accompanied by the loss of electron. Do you see over here? Originally, this one have the electron. After oxidation has occurred, it has kicked out the electron. Electron has been lost away. On the other hand, reduction reaction, this thing originally don't have electron. I throw 2 electrons inside. Then the reduction reaction will occur to form the copper solid. This nicely brings us to the next page, on page number 5, where we can fill in the blanks. Okay? So oxidation and reduction in terms of electron transfer. Okay, so just now we ascertained that when the reaction, okay, goes from copper to copper 2 plus, when there is a loss of electron, we will call this an oxidation reaction. Loss of electron is considered an oxidation reaction. On the other hand, reduction is the gain of electron. It's the gain of electron, okay? Now, I'm going to share with you a small part of a story, which I'm going to wrap it up during the end of the class, okay? So let's give you the story first. Let's tell you the story first. Now, it was a mnemonic for people to actually learn this by using this term called oil rig. Okay, so it was a long time ago. Okay, there was this guy, okay, who went onto the oil rig, okay, which is basically a particular like a crane like that, okay, located to mine up, okay, all the oil from the grounds. And what happens is that all these oil rigs, okay, which help to generate the oil, okay, they are actually have a lot of chemical reactions there. And somebody came up with this brilliant idea to turn this into a mnemonic, okay, for us to remember very easily. So what is the term oil rig actually represents? So it tells us that oil represent oxidation is loss and rig is reduction is gain. So in case you cannot remember this, you remember oil rig, then oxidation is the loss of electron, whilst the reduction is the gain of electron. Okay, so oxidation is a loss of electron once again, and reduction is gain of electron. So if you cannot remember, just remember oil rig. Okay, part 2 of the story coming up later. All right, let's try out. Okay, this so sorry. Okay, there's another continuation to this. In electron transfer reactions, one substance is going to give up the electron, which means it loses the electron and is hence oxidized, and another substance takes in the electrons, okay, which means that it gains the electron and is defined to be reduced. Can everybody? So don't get confused. Electrons is loss is oxidation, gain is reduction. Can? Okay, now let's look at an example. This question is very familiar, don't you think? This question? Because just now we look at this question as well, but we explain this in terms of oxygen. Now let's try another method. Let's explain the redox reaction in terms of electrons. Now, let's read the question together once again. Aluminum burns in oxygen, forming aluminum oxide. So over here, what you can see is the reaction over here. I'm going to use color coding again. We have Al, Al. We have oxygen and oxygen. Now you can see over here that before the reaction, aluminum has no oxygen, and at the end of the reaction, aluminum has oxygen. But what we can also deduce from here is that this is metal, okay? This is a metal, okay? And the predominant bonding in this is known to be metallic bonding, okay? Whilst when we look at Al2O3, okay, it is going to be an ionic bonding because metal plus non-metal is ionic bonding, right? So in this case, what is the first thing to do? Always first thing to do is to identify the ions present. Okay, so let's try to identify the ions in this particular reagent over here. We have Al2O3. We can break it up into Al3 plus and O2 minus. So these are the ions that we have already known previously, Al3 plus and O2 minus. Is that okay, everybody? So you can notice over here that I'm going to highlight to you the color coding again. From the left-hand side of the reaction to the right-hand side of the reaction, do you notice that aluminum from 0, it becomes positive 3. Now, this is accompanied by what? A loss of electron. Do you agree with me? For me to become positive, I need to lose electron. I need to lose the negative charge for me to become positive. So aluminum, when I lose electron, what is it undergoing? It is actually undergoing an oxidation reaction. Okay. Now, on the other hand, when we look at oxygen, oxygen originally has not many electrons, therefore it's neutral, but after the reaction, it's now minus charge. And this means that it has gained electrons, right? So this over here, I will term it, okay, to be a reduction reaction because it has gained oxygen atom. It has gained electrons. Okay, so I say again, because it has gained electrons to become negative, therefore it is a reduction reaction. Okay. So electrons are transferred, okay, let's read here. Electrons are transferred from aluminum to oxygen to form aluminum ions, Al3 plus, and oxide ion, which is O2 minus. So just now I said already, what is the one that loses electrons? The one that becomes positive is the one that loses electron, right? So aluminum loses electrons. Therefore, it is undergoing oxidation. Whilst we also can observe that oxygen gains electrons, hence it has undergone reduction. Can everybody? So you see how electrons are actually very powerful. It can actually help us to deduce whether something is oxidized or something is reduced. Okay, so remember, oil rig, oxidation is the loss of electron oxidized, and reduction is the gain of electron, so gain electron, reduce. Okay, everybody, any questions? Please feel free to type into the chat if you have any questions, or you can unmute yourself as well. Okay. I know a lot of you are very shy, so don't worry, you can just type your questions into the chat as well. Okay. All right, let's move on to the next page, okay, which is on page number 6. Now, this part over here is the most challenging part, okay? Concept number 6 is reduction and oxidation in terms of oxidation state. A lot of students face trouble when doing this. I tell you, a lot of students, seriously, a lot of students face trouble when doing this. Now, what is the guiding principle behind the term oxidation state? Okay, let's go back to this reaction over here, the A and B reaction on page number 4. Let's come back here. Okay, I'm going to clean this up a little bit and show you what I mean by oxidation state. Okay, first off, I'm going to erase off the electrons. Okay, let me just erase off the electrons first. Okay, now we know that, okay, previously we have learned that okay, ions, right? Okay, they have a certain charge to it. Even if they are inside an ionic structure, for example, MgO, okay, they have a certain charge to it. Now, what happens is in the usage of oxidation state, we are going to use this charge to help us determine what is undergoing oxidation and what is undergoing reduction. Okay, let me illustrate to you this idea with the example of magnesium to magnesium oxide and copper oxide to copper. Now, just now we have agreed with ourselves that magnesium exists as 2+ ion and copper exists as 2+ ion when it's in ionic, right? When it's in an ionic lattice or is it ionic structure. Now, what happens is you will notice over here that magnesium originally it has 0 charge. After the reaction, it has now 2+ charge. On the other hand, copper originally has a 2+ charge. After the reaction, it has decreased to a 0 charge. Now, the term oxidation states refer to the charge of the species, okay? So you must write down with me over here. The term oxidation state, okay, refers to the charge, okay, on a species. Whether or not is it an ion, is it an atom, okay? Now, you can see over here that this tells me that magnesium has a 0 oxidation state. And this one over here has a +2 oxidation state. You can see that copper 2 oxide over here, the copper has a +2 oxidation state, and the copper over here without anything has a 0 oxidation state. So let's look at this carefully. 0 to +2, if there is an oxidation reaction, what happens? The oxidation state increases. Agree with me? Oxidation state will increase. On the other hand, if it's going from +2 to 0, the reduction reaction takes place. When there is a decrease in oxidation state, it is termed to be an reduction reaction. Okay? So let's consolidate what we have just learned in page number 6. At the top over here, okay, the increase in oxidation state is an oxidation reaction, whilst the decrease in oxidation state is termed to be a reduction reaction. Okay? So oxidation reaction is when the oxidation state has increased. Before the arrow, it is smaller. After the arrow is bigger, then oxidation has occurred. If the oxidation state decrease, which means before the arrow is bigger, after the arrow, the oxidation state is smaller, then reduction reaction has occurred. Okay, once again, to re-emphasize again, what is the term oxidation state refers to? It is the number of the charge on an atom if it has existed as an ion. Now, there are some rules to this particular thing over here, the oxidation state over here, and I would like to go through with some rules, okay, for this kind of reactions. But first off, I need to tell you why is it that just now while we learn oxygen, while we learn hydrogen and electrons, they are not so useful. And oxidation state over here this one over here is the most powerful one. Why is this the most powerful? Okay, I'm going to show you now. Now, let's look at this reaction over here. In this reaction over here, we look at how hydrogen is actually reacting with oxygen to form water. Okay, so hydrogen and oxygen. I'm gaining hydrogen, I'm gaining oxygen at the same time. So am I undergoing oxidation or reduction? Is this a redox reaction? I have no clue. Therefore, the most powerful way for us to understand this is through the use of oxidation state. Okay, so in some reactions, we are unable to explain the oxidation and reduction reactions via the transfer of electrons or the loss and gain of hydrogen and oxygen. For example, the reaction that involves only atom or molecule. All right, let's look at some of the rules for the oxidation state. There are 5 golden rules in total for oxidation state. Okay, let's look at these 5 one by one. Let's look at the first rule first. Now, OS over here simply means oxidation state. Okay, so oxidation state, OS. Now, rule number 1 states that the oxidation state of free elements equals to 0. Okay, what does this mean? Free elements equals to 0. Now, you imagine for me that I am actually now holding a piece of, for example, copper metal. Okay, I have copper metal over here. Imagine this is a copper metal. Now, copper metal that has no impurity, no nothing, is pure copper metal. Okay, so if I say that there is a copper metal, okay, the oxidation state of all the atoms on the copper itself is 0. That is 0 oxidation state. Okay, so the oxidation state of copper is actually going to be 0. If let's say I have iron, if I have a block of iron that is just pure iron, the oxidation state on it is also going to be 0. So this is what is meant by free elements. It is pure, it has nothing inside of it, it's not bonded to anything itself, it is just it itself in its elemental form. Now, nitrogen, on the other hand, okay, is also a free element. Okay, nitrogen atom, okay, when there are 2 atoms together, is a nitrogen molecule. And what happens is that this nitrogen molecule, okay, is only made out of nitrogen itself. Therefore, the oxidation state is also 0. Okay, same applies for oxygen. Okay, look around you, there's gases, there's oxygen gas in the atmosphere. The oxidation state is 0. Okay, because it is just the element oxygen itself. Next, let's look at rule number 2 to help us deepen our understanding on oxidation state. Now, rule number 2 states that the oxidation state of simple ions, okay, simple ions, right, is equivalent to the ionic charge. Okay, is equivalent to the ionic charge. Now, what does this mean? What does this particular thing over here mean? Now, the simple ions and ionic charge simply refers to if I have an ion, what the charge on the ion is going to be equals to the oxidation state. So for example, if I have copper 2+ over here, the oxidation state of the copper is going to be +2. Now, I want everybody to write this down, okay? For oxidation state, okay, the number is always following, okay, the plus or minus sign. So if the charge is plus, if it's copper 2+, then the oxidation state will be +2. This is very important. If you write 2+ as the oxidation state, you will be marked wrong. Okay, you must understand this, that the oxidation state, always the sign comes first, followed by the number. All right. Now, what about oxygen or oxide ion? Okay, so you see oxide ion over here. So this one over here is simply the ionic charge as well. It's going to be 2 minus, which is going to be translated to -2 in terms of oxidation state. Okay, so I'm going to give you a few examples to help you to deepen the idea. Okay, I'm going to write a few down over here. Then you must tell me individually what is the oxidation state. Okay, now I give you 4 over here. 1, 2, 3, 4. Okay, can you please write this down onto your paper and try to actually find out what is the oxidation state of each element, okay, in each of the compounds. So for example, I do the first one for you, Al2O3, okay, aluminium on its ion is Al3 plus. Therefore, the oxidation state of Al is going to be +3. Oxygen is O2 minus. Therefore, the oxidation state is going to be -2. Now, can you do that for the rest of these 3 over here? Okay, if you have not enough space, you can actually go down, okay, to the bottom of the page or the next page, the top of the next page, for you to write out your workings as well. There's an empty space at the over here as well. Okay, there's an empty space over here. I give you another 1.5 minutes to try and figure out the oxidation states of each of the elements over here in each of these compounds. Okay, so follow rule number 2 first. Okay, don't read the other rules first. You may get confused by them. Okay, so if you're done, you can look up for the answers. But for those who are still doing, no worries. Continue doing. Okay, I've done some color coding for you. Okay. So let's look at copper oxide first. Okay, let's look at copper oxide first. Now, copper oxide, okay, we know that copper, this is an ionic compound, right? Because metal plus non-metal. Agree with me? So we have copper over here, which is +2 charge, and oxygen over here, which is -2 charge. So therefore, the oxidation state of copper is +2, and oxygen is -2. If you look at NaCl over here, sodium chloride, you can see that sodium is going to have a sodium plus charge, and chloride is going to be -1 charge, and it will correspond to the oxidation state as well. Okay, so we have KOH as well, where potassium is +1, okay, and oxygen is -2, and hydrogen is +1. So always remember that the oxidation state belongs to the element itself, okay, and not, okay, it doesn't belong to, for example, OH minus ion, okay? So it is the element itself. Okay, if I all go with this, okay, let's look at rule number 3. Now, in rule number 3, we are looking at oxidation state of elements in a compound, okay? So elements in the compound is fixed. The oxidation states of elements in the compound is fixed. Now, Why I want you to remember this is because when you are doing question, you can actually identify, okay, if you are given a very difficult molecule. For example, I give you CuSO4. This is not that difficult, but I'm asking you, okay, can you please find out for me what is the oxidation state of S? Okay, then you have a problem, right? Okay, because you don't know what is the what is the formula for you to do this, or what is the method for you to do this. Okay, so let's explore how to do this first. Now, in rule number 3, we are told that hydrogen in most compound, the oxidation state is +1. Okay, because H plus ion, remember in acid and bases, we always dissociate to form H plus ions. Acid always dissociate to form H plus ions. Oxygen in most compounds, it has -2 charge. Why is this so? Okay, remember when you draw out oxygen, it has a configuration of 2,6. For me to go to noble gas configuration, I need to gain 2 electrons, and electrons are negative. Therefore, it's going to give me O2 minus ions. This is a stable form, and that's the reason why it is -2. Okay, so you don't memorize it. Okay, understand through the chemistry. Okay. Now, all group 1 elements, the oxidation state is +1. Okay, all group 1 element, for example, potassium, for example, sodium, for example, lithium. Now, the last one is all the group 2 elements, the oxidation state is +2. The oxidation state of all group 2 element is +2. Okay, so it's basically its ionic charge. Now, let's move on to rule number 4. Now, rule number 4 is something that I've already taught you just now. The sum of oxidation state in an element of a compound, okay, is equals to 0. Now, what does this mean? If I give you something that has 0 charge, I give you something that has 0 charge, right? All of the elements inside of it plus together must give me 0 charge as well. Okay, so makes sense, right? I give you something that has 0 charge, you must prove to me that it is 0 charge, right? So, for example, Al2O3, okay, everything added together, aluminum is 3 plus, oxygen is 2 minus, times 2 plus times 3, okay, and you will get 0 as well. Okay, then for water, okay, I have a question over here. I'm going to go back to it in a while. So sorry. Okay, let's look at water. Now, water, the sum of the oxidation state in a compound is H2O. Okay, it's going to be 0 as well because water is neutral. There is no charge on it. And last but not least, magnesium oxide. Okay, we know that this is a compound as well. 0 charge is neutral. And Mg is going to have +2, O is going to have 2 minus or -2. Okay, I have a question over here in the chat. Now, the question is for the KOH oxidation state. Now, why is it that, okay, I separated out oxygen and hydrogen oxidation state? Why is it not OH minus and 1 oxidation state by itself? This is a very good question, and it shows that, okay, you are thinking about why the chemistry, okay, behind why we talk about oxidation state in this certain manner. Okay, so for this question, I want to draw your attention back to the definition of oxidation state, which is the charge it would have if the atom existed as an ion. Okay, so you see over here, if I have KOH, now I know that this is an alkali. I know that. Okay, we all know that, right? Now, we also know that alkali, they are going to dissociate to give us OH minus ion, right? OH minus ion and H plus ion, K plus ion, okay? This is a K plus ions and OH minus ions. Now, why is it that since this is one molecule, why is it that I'm going to separate out into O and H? Now, this molecule over here is made up of both oxygen and hydrogen. Okay, agree with me, both oxygen and hydrogen put together, that's why I got one OH minus ion, right? So what happens is that oxygen is an element, hydrogen is another element. Both of them have their different oxidation state, which their net total led you to get this -1. Okay, so we have oxygen is what? Oxygen is -2. Okay, as mentioned just now in rule number 3, oxygen in most compound is -2, and H is always +1, and that is the reason why the total of -2 and +1 is -1. this negative one apply to the whole OH. Okay, it doesn't just apply to hydrogen or oxygen. Okay, very good question. Yeah, that's for OH minus. Okay, any other questions from anyone? Okay, so I'm going to move on to example. Okay, I'm going to move on to rule number 5. Okay, rule number 5 is the one that is corresponding to what Ro has just asked. Okay, so let's look at this. The sum of oxidation states of elements in an ion is equal to the charge on the ion itself. Okay, so OH is also here, OH minus is also here. So you can see how in OH minus, okay, I want to stress this once and for all again. The fact that ions, okay, exist, which means that there is a charge on the ion. The charge itself is not on one element, but the charge is for the whole ion. So 2 minus is applied to the whole SO form ion. The negative charge here is applied to the whole NO3 ion. Okay, it's not to that one specific oxygen or that one specific element. Okay. So for those of you whose foundation is not that strong yet, okay, this is a revision for you. And for those who already know this, then okay, it's a reminder. All right, let's look at OH first. Let's look at OH minus first. Now, OH minus, I'm going to simplify this very easily for you. Now, the sum of oxidation states of all the elements in an ion must be equal to the charge, right? So therefore, oxygen, when it's minus 2, I have how many oxygen? 1 oxygen. So I got 1 times minus 2 plus 1 times plus 1 because hydrogen is plus 1. It will give us minus 1, which is corresponded to the oxidation state over here. Okay. Now I want to show you how to calculate oxidation state of unusual elements. For example, this one over here. Now, sulfur is something that I'm not very sure because sulfur is not in my rule number 3, right? It's not in my rule number 3. It doesn't tell me what is sulfur, right? So let's give it an arbitrary number. Let's say that oxidation state of sulfur is X. Okay, give it X. So those of you who are not so good in math, okay, don't worry, follow me. If I have X plus 4 times, okay, oxygen is how many? Minus 2, right? Remember, oxygen is minus 2. And this will give me the total charge on the molecule, which is 2 minus, okay, minus 2. Then very conveniently, what I can do is I can do some math. Okay, X will be equals to minus 2 plus 6. Okay, so sorry, it's not plus 6, it's plus 8, so sorry. And this will give us a net charge of positive 6. So what happens is now I can deduce out the oxidation state of unusual elements. So for example, like sulfur, now I know that sulfur oxidation state is going to be plus 6. Now with this in mind, can you help me to try out NO3? Now I want you to find out what is the oxidation state of nitrogen for me. Is that okay, everybody? Let's try this out. Using rule number 5, where the sum of oxidation state of an ion is equal to the charge of the ion. Okay, let's try this out. So I'm going to just say that it is X first, okay, and the rest you can try. Okay, so if for NO3, you can look up if you are done, check your answer. And for NH4, okay, so once again, I will do this for you. I'm so sorry, this is 4. Okay, so you can try out NH4 first before looking at the answer. Okay, so you can see NO3 over here, we have X as nitrogen plus 3 times -2, which is the charge on oxygen, which is the oxidation state on oxygen, and equals to the sum, which is the charge -1. If I do some simple mathematics of recalculating everything or rearranging everything around, you can see that nitrogen has a charge or the oxidation state of +5. Then when we look at ammonium ion over here, I will assign this X. Then if I sub in the values, okay, X plus 4 times +1, because hydrogen is +1, equals to total of +1, then X will be equals to -3. So nitrogen has oxidation state of -3. So you can see that this is nitrogen, this is also nitrogen, but the oxidation state in different compound or different ions are different. Okay, they are not the same, they are different. So different type of ions have the elements inside different type of ions can possess different oxidation states. So what is the moral of the story over here is please don't memorize because you don't know which elements the oxidation states are what. So you can see, oh, I remember, oh, for example, nitrogen is +5. Then in this case over here, nitrogen is not +5. Then how? Okay, so you must be able to learn the rules for you to derive the oxidation state of each of the ions. Is that okay, everyone? Please let me know if you need more time to copy down. I will flash the answer for longer. Okay, if you're all good with this, okay, can I have you to go to the next page on page number, what page is this? Page number 6. Okay, go to page number 7 and okay, try out the question, example 5 on page number 7. Or before you do example 5, maybe never mind. Let's do example 6 first. Example 6 is easier, okay? Let's look at question number 6 first. Instead of question 5 first, we look at question 6 first, okay? Yeah, I will give you the answer for this one for a bit longer in case for those who still needs this. Okay, can we try out question number 6? We will go through example 5 later. Okay, let's look at question number 6, part A first. We are asked to calculate what is the oxidation state of the underlying elements in the following compounds or ions. Now, sometimes, right, when we look at some questions like this, it is quite easily for us to be tricked, right? Because we have already this muscle memory, okay? A lot of us have this muscle memory of, oh, this should actually be +2, or is it +2? I think last time I did this question, it was +2. Now, in this case, for redox reactions chapter, I don't want you to rely on your muscle memory, okay? Because many a times, right, the questions are so dynamic, they can change very easily. And sometimes you remember things, remember wrongly, because different elements possess different oxidation states in different compounds, right? So let's look at part A first. Now, part A, we are looking at NH3. So NH3 is ammonia. And what rule am I going to apply over here? Now, I'm going to apply the rule that the sum of the oxidation state, or the total oxidation state of all the elements, will equals to 0. Okay? So you must first be able to tell me that the sum of oxidation state must be equals to 0. Because this is a compound of 0 charge, then the sum must be equals to 0. Then you must tell me, okay, the sum of individual must be equal to 0, right? So I don't know, N, I put X. So X plus, I got 3 times hydrogen. Hydrogen is +1 equals to 0. And from this, very conveniently, we can actually solve that hydrogen, the nitrogen, okay, is going to have oxidation state of -3. Now, the next one over here is KMNO4, potassium permanganate, very popular oxidizing agent, very popular titration reactant, right? Now, in this part over here, we are asked to find out what is the oxidation state of Mn, manganese, right? So sum of oxidation state, once again, I'm going to apply the rule that the sum is equals to 0. And since I don't know what is Mn, I'm going to put X. So potassium is a group 1 element, it's going to have +1 plus X, and I'm going to have plus this one also, -2 equals to 0. Therefore, if you do some simple mathematics, you will realize that X is going to be +7. Is that okay, everyone? Now, CO3 2- is one that some students may actually not be able to visualize at the first glance. Okay, but of course, with sufficient practice, okay, if you expose yourself to the correct materials and resources, and when you are doing questions very diligently, you will be able to get the answers very quickly, okay, and correctly as well, of course. So this one, I'm going to apply the sum of oxidation state will be equal to its ionic charge, right? So sum of oxidation state will be equals to what? -2. Agree with me? Because the charge is 2-, sum of oxidation state is -2. Can now? So carbon, if I don't know, I'm going to give it X. Therefore, X plus 3 times -2 is going to give me a total of -2. And doing some simple mathematics, this will give me X equals to +4. And therefore, the oxidation state of carbon is going to be equals to +4. Is that okay, everyone? Okay, so this is how you actually be able to calculate the oxidation state very quickly by giving an arbitrary value to those that you are trying to calculate. Okay, so if you're done with question 6, can we go on to question number 5? This is it's a more of a challenging question. Okay, so if you're done with question number 6, let's go on to question number 5. We are looking at potassium dichromate, which is something that most of you are not very familiar with. Okay, if you still need time to copy the answers. Okay, so potassium dichromate, if you are unable to get the answer, try to remember what are the 5 golden rules that we have introduced for redox reactions. Okay, for oxidation state, what are the 5 rules? Then you apply one of the rules individually, then you will get the oxidation state quite quickly. Okay, so I want you to try out question number 5 or example number 5. Okay, and type your answer into the chat. Okay, type your answer for question 5 into the chat. Okay, if you need any hints, you can look at the screen. Okay, Jasmine says it's +6. Does anyone have any other answers? Okay, Amanda says +6, okay. Okay, oxidation state of chromium, right? Oxidation state of chromium, which is CR. Okay, Natalie says same too. Okay, very good. Okay, so the rest of us, I think we are on the way, on track to getting there. So, okay, let me explain to you how to get the answer. Now, I know that chromium is the one that I want to find, so I'm going to give it a value of X. Then, okay, since I know that K2Cr2O7 is a neutral compound, there's no charge to it, then the sum of oxidation state must be equals to 0, right? So this is the one that we are always fall back onto when we are looking at compounds. All right, so I can write out the sum of oxidation states. I know that potassium is +1 because group 1 times 2, plus I got 2 times X, plus I got 7 times oxygen is -2. This gives me 0. If I work this out, okay, it will actually give me 2x minus 12 equals to 0. If I do some manipulation, I can get x equals to +6. Okay, so congratulations to Ro, Jasmine, Amanda, and Natalie. Okay, all of your answers are correct. Okay, so oxidation state of chromium is going to be +6. Okay, so if you're all good with question, example number 5, let's look at advanced redox reactions and oxidation state. Okay, so this part over here is a little bit more advanced, okay, as the name suggests. Advanced advanced redox reactions and oxidation states. Now, we have understood earlier, right, that oxidation happens when it is defined as an increase in oxidation state, right? So oxidation state increase, oxidation. Decrease in oxidation state, reduction, right? So let's highlight this first. Now, I want you to look closely at this reaction. Okay, I want you to look closely at this reaction. Now, in this reaction, right, you notice that we have zinc reacting with H2SO4, forming zinc sulfate and hydrogen gas. Okay, so you realize that, oh, this reaction a bit difficult, right? Because I cannot see anything. It's too many things for me to see, right? So, moral of the story: simplify things down. Once again, I want to highlight again what is the first step. Always identify what are the ions present. Always identify what are the ions present. Okay, so ions present over here, I have H+, which means that hydrogen has +1 oxidation state. Now, on the other side, okay, what are the ions present? I have zinc. zinc is plus 2 oxidation state because zinc 2 plus. Now, very good that some of you pointed out that just now, the ions, right? Why is it that I don't consider ions in some reactions? You will notice that SO4 over here is repeated over here. So therefore, I have no need to consider SO4. I have no need to consider SO4, right? Because it's already the same thing, SO4 2 minus on the left-hand side of the equation and the right-hand side of the equation, they are exactly the same. So I don't bother about it, okay? So let's apply our rules. I know that zinc, this over here is free element. According to rule number 1, the oxidation state is 0. Okay? Now, hydrogen, since the sum of this together must be 0 because this is compound, okay, rule number 3, you must be able to identify the fact that SO4 is 2 minus would mean that hydrogen is going to be plus 1, okay? And next up, we look at this one over here, zinc sulfate. Zinc is plus 2. And this one over here, hydrogen is free element again, right? Free element, nothing else, hydrogen only is going to be 0 as well. So let's write out what is the changes in oxidation state. You can see that zinc from the left-hand side to the right-hand side, what happens? Zinc from the left to the right, okay, before the arrow to after the arrow, it has undergone, okay, oxidation, right? Because there is an increase in oxidation state. On the other hand, from hydrogen is plus 1 to hydrogen, which is plus which is 0, this over here, you have seen a decrease in oxidation state, and it is a reduction reaction. Okay, so I'm going to label this for you over here. This is an oxidation reaction, and this one over here is a reduction reaction. Okay, so sorry, to be exact, it should be pointing to the hydrogen. All right. So let's talk about answering techniques. So why is answering techniques so important in chemistry? Okay, why is answering techniques so important in chemistry? Okay, I understand the equation is not balanced. This 2 should be eliminated from the reaction. Okay, so sorry, can you please cancel away this 2 over here? All right. Once again, I would like to stress again that for redox reactions, okay, we only care about, okay, the reactants and the products, and we don't really need to bother about the mole ratio between each of the reactants, okay? Anyway, back to my point on answering techniques. Now, for answering techniques, why is it so important? Now, you remember in mole concept, right? Mole calculation chapter that you have learned maybe around 4 to 6 months ago. Mole calculation chapter is a little bit challenging for some of you because you have a lot of formula to memorize, okay? Now, but if you do not have the correct way to remember the formula, okay, it is not just simply copying so many times the formula until you understand, until you finally get it into your head. You must understand why a certain formula work in that manner, right? So that is the reason why answering techniques are so important, because it helps you to link the formula to the concept, and it helps you to link the concept to the application, right? Without the correct concept, you cannot understand the question. Without the understanding of the question, it is going to affect how you answer the question and your formula that you're going to use for the question. Okay, and this is the reason why answering techniques are very, very crucial, and I want to train you on answering techniques during the session today. Okay, now there is a standard format, right, or SOP, okay, for us to actually write out the answering techniques for redox reactions. Okay, so how do we actually answer? Very simple. Let's look at zinc first. Okay, let's study zinc first. Zinc from the left-hand side is going to be 0 oxidation state, 2 plus 2 oxidation state, right? So therefore, you must tell me first what is being oxidized. Okay, so zinc is being oxidized. And why is it oxidized? Because, explanation, increase in oxidation state of zinc. Originally, it is 0. 0 in zinc, 2 plus 2 in zinc sulfate. Okay, so this is how, okay, you actually score your full marks in the exam, because you no longer have to don't know what to write for the question. Okay, so you must, for example, this question would be explain why this is a redox reaction. Okay, so you must tell me this thing is oxidized because there is an increase in oxidation state from 0 to +2. Now, hydrogen, on the other hand, you can see clearly over here is getting reduced. Now, why is it reduced? Because from here, you can see that originally hydrogen oxidation state is +1. Now it becomes 0, right? So there is a decrease in oxidation state of hydrogen from +1 in H2SO4. You must tell me in what, because I don't know which 0, where is the 0? The 0 is in zinc itself. Okay, 2, okay, what is it? 0 in hydrogen gas. Okay, once again, I want to stress the fact that state symbols are very important in this chapter. All right. So this is the answering technique required for you to score the full 3 marks for this question. In your O levels, this question will be worth 3 marks. Okay, so 1 mark to tell me correct oxidation and reduction, and 1 mark for each of the explanation. Okay, for your prelim exam or your internal exams, normally this question will only be 2 marks. Okay, because sometimes schools are very stingy on the marks, right? So they give less. Okay. All right, you must take note, right, that in this reaction, once again, I stress the point that the sulfate ion does not change, and therefore we do not consider, okay, the reaction of the sulfate ion, because sulfate ion is here and here, nothing has changed. We just leave it as it is. All right, any questions? Okay, feel free to ask if you have any questions. I'll leave this here for a little while more for those of you who want to copy. Okay, so if you're done with this, okay, I'm gonna give you a while, okay, to try out the next question, okay, which is question number 7. It is a little bit of a challenging question for those of us who have just started learning this chapter. Okay, so if you're all good with this, let's take a look at question number 7. I'm going to give you some time to do this question first. Okay, let's try out part A first, followed by part B, shall we? Okay, let's go through the question, shall we? Now, in this question, we are given that small amount of sulfur dioxide are added to wine as the preservative. Okay, sulfur dioxide content can be found using the reaction with aqueous iodine. So in this reaction, we are given that SO2, okay, is actually transformed into SO4. And okay, you realize that okay, this particular thing over here is not charged, which means a compound, and this thing over here, which is charged, is an ion. Right. So in part A, we are asked to state the oxidation state of sulfur in SO2 and SO4, 2 minus. Okay. So how we go about doing this is very simple. Let's just apply the rules that we have learned earlier. The sum of oxidation state in a compound is equals to 0, or the ionic charge in an ion will be equals to the sum of oxidation state. Okay, so you can see how in SO2, I use X to represent the oxidation state of sulfur, followed by 2 times -2, which is oxygen's oxidation state, equals to 0. Therefore, X will be equals to +4. Now for SO4 2 minus, on the other hand, we have X plus 4 bracket -2, which is the oxidation state of oxygen, equals to the sum or the charge on the ion, which is -2, and it is going to be +6. Hence, you can state and explain whether sulfur has been oxidized, okay, or reduced in the conversion of this reaction. Okay, so let's try out part B, okay? Let's try to write out the answer following your answering technique. Okay, so you can see that sulfur is oxidized because there is an increase in oxidation state, right? So you can increase in oxidation state, right? So I'm going to write down here, increase in oxidation state from +4 in SO2 to +6 in SO4 2 minus. Okay, so this kind of question, okay, is quite standard. You must be able to explain well. The answering technique, okay, you must remember by heart, okay, must remember by heart what is the answering technique required. And okay, so extension to this question, okay, I will give you a part C, okay, since this question is stopped at part B. Now I want you to identify, okay, what is the what species have been reduced, okay? What species have been reduced? Okay, and explain, okay, with reference to oxidation state. Okay, what species has been reduced? Okay, let's try this question as well. Okay, you must look at the equation. Look carefully at the equation and tell me what species has been reduced. If you have any question, please let me know inside the chat so I can answer that. Okay, so if you need a little bit of help, okay, let's look at the left-hand side of the equation followed by the right-hand side of the equation, okay? So left-hand side of the equation, you can see that, okay, what are the two other things that we have? We only have I2 and H2O, right? I2 and H2O. And on the right-hand side, I have I minus and H plus, I minus and H plus. So you can see over here that I2 is a free element, okay? Free element oxidation state is what? 0, right? Remind yourself, free element oxidation state rule number 1 states that it is equals to 0. Now, I minus, on the other hand, is an ion. So the sum of it is equals to its ionic charge. Therefore, I has charge of -1 or oxidation state of -1. So you can see over here that O to -1, I to I minus is from 0 to -1. And that is the reason why what has been oxidized is iodine. Okay, iodine has been reduced, reduced, okay, decrease in oxidation state, okay, so 0 to -1 is a reduction process. Follow your standard answering technique. We have a decrease in the oxidation state. Okay, please don't use short form. I'm using short form to reduce, okay, the words that I have to write. Okay, I mean oxidation state short form, don't put OS, okay, just spell it out. Okay, but for the elements, you can just put S and I is okay. From, okay, 0 in I2 to -1 in I minus. Okay, so this is how you answer the question for part C. Okay, so give you some time to copy down this answer. And we want, okay, I also want to highlight something after you copy down the answer, okay, about the water molecule over here. Now, one thing about many students is that they don't really try to think of the questions in the context of the question. Okay, what do I mean by this? Now, if we look at the two things that are highlighted in yellow over here, I have water and H plus over here on the left-hand side and right-hand side respectively. And what happens is some students may think, isn't water oxidized? Isn't the hydrogen oxidized? You see, now this one is 0 charge and this one is positive charge. Then some people say, oh, Mr. Ko, why is it not that this is getting oxidized to H plus? Now, let's try and understand over here again that the charge on the whole compound does not necessarily have to correspond to whether or not one species is very low in oxidation state or very high in oxidation state. You see over here, when we look at SO2 and SO4, we know that SO2, sulfur is +4, but this whole thing is minus, right? But sulfur is still +6. So this minus charge does not tell me anything about the oxidation state of sulfur. You must be very, very clear on this first. Okay, and water to H plus, you can see how, right, that oxygen is always -2, hydrogen is always +1. Therefore, hydrogen, since it's +1, to here is also +1. There's no change in oxidation state. This remains unoxidized or not reduced as well. It just remains as +1 oxidation state. Okay. All right. Any question? Okay, if you have no question, I would like to draw your attention back to page number 2, where we still have a table that we want to fill up, okay? Now we have a shoe method to ace the redox question where I'll complete the story. All right, let's talk about oxidation and reduction, okay? So oxidation and reduction, once again, you must be able to tell me, okay, how what each of these 4 factors mean in terms of oxidation and reduction. And I call this the shoe method, okay? where it's very easy for us to memorize. Very easy for us to memorize and for us to understand as well. Okay, so this is actually listed in the priority of which one I use, 1, 2, 3, 4. In every situation, I will try to use oxidation state to answer first, followed by hydrogen, oxygen, and electron. Oxidation state is my best friend. I will always use oxidation state to answer first. Okay, why is it called the shoe method? Because it's state, hydrogen, oxygen, electron, easy for you to memorize as well. Okay, now, oxidation state, once again, is defined, okay, as the charge of an atom if it existed as an ion, right? So an increase in oxidation state means that oxidation or reduction, oxidation, right? So increase in oxidation state is oxidation, and a decrease in oxidation state is reduction. Okay, fill in this table with me. Now, then we look at hydrogen. Now, hydrogen is a little bit opposite of oxygen, okay? Hydrogen is when its loss of hydrogen is oxidation and gain of hydrogen is reduction. For oxygen itself, it is the opposite of hydrogen. Gain of oxygen is oxidation, and the loss of oxygen is reduction. And last but not least, electron will always be loss of electron is oxidation and gain of electron is reduction. Okay? So you must see the correlation. Oxidation state and oxygen are the same. When increase is oxidation. When decrease is a reduction. But I do not say there's a gain in oxidation state. I don't say there's a gain in oxidation state. I don't say that there's a loss in oxidation state. I say increase and decrease, okay? So this is the keywords you must use in your answers. And for hydrogen and electron, they are the same. So loss of electron and loss of hydrogen is oxidation and gain is reduction. Okay, so how do you remember this? How do you remember oxidation and reduction for hydrogen and electron? So remember always, he works on an oil rig. Okay, so oxidation is loss, reduction is gain. This guy works on an oil rig. He, hydrogen, and electron. Okay, hydrogens and electron is always oil rig. Oxidation is loss of hydrogen and loss of electron. Reduction is always the gain of hydrogen and gain of electron. So this is how you remember. Okay, so this is how the story ends. Okay, a bit lame, but it gets the idea across, right? Okay, so this is something that you must remember for oxidation and reduction. Okay, he works on an oil rig. So hydrogen, electron, you must follow. Oxidation is loss, reduction is gain. For oxidation state and oxygen, increase, decrease, gain, and lose. Okay, so this is your shoe method. Now in exam, right, I don't want you to spend time writing out this table. Okay, it's really very time consuming. I want you to do this. Okay, for some students who like to save time, just write SHOE out. Okay, write SHOE out. Write O on top, R below. Okay, so you put plus, minus, plus, minus, minus, plus, minus, plus. What does this mean? You see over here, oxidation state. Positive means oxidation, negative means reduction. Hydrogen, the loss is oxidation, gain is reduction, right? So oil rig, right? Okay, so you write this down, and then you are able to actually deduce the table very quickly. Okay, so exam techniques for you. Okay, so please copy down this. Give you a while to copy down this before the next part, which I'm going to tell you about how we strategize the best, okay, for you to ace your exam. Okay, so this part over here is just simply a summary. Okay, go back and take a read of this, as well as the pages, okay, of different type of factors, which is oxidation state, hydrogen, oxygen, and electron. These are the 4 factors that affect whether something is a redox reaction or not. Okay, so with this in mind, okay, I would now like to do some sharing on the how we strategize for our O levels. Okay, so back here already. So let's go ahead and look at how we best strategize. Okay, so to the O levels, we have 11 months. Okay, we are in December now. Okay, O levels will be in October next year. We have 11 months to go. And what do you want to make the most out of this 11 months? Let me show you, right? Why is it that a lot of students face a lot of difficulty when they're studying chemistry? And for ourselves, we have gone through the system already, and we are the best. We are the most suited to give you some advice on this particular area over here. Now, let me try to outline to you what is the roadmap that is going to be taken. Okay, so you realize that, okay, in 11 months to go, what is the roadmap is? In December, you actually covered all your Sec 3 topics already. For example, mole concept, for example, chemical bonding, ionic bonding, metallic bonding, all these bondings. And you will also see how you learn about metals as well as a periodic table as well. Now, after that, your school confirm will have given you some topical practices as well, okay, all your worksheets, all your past year papers, and for you to strengthen your foundational concept. All your Sec 4 topics, or majority of those, okay, will actually build on or require a little bit of knowledge of the Sec 3 topics before we can do the Sec 4 topics. For example, you remember acid and bases. In secondary 4, around 40% will be dedicated to organic chemistry. And what happens is that in organic chemistry, there will also be acids, right? So you must be able to grasp the idea before we go on to secondary 4. Now, in next year, January to April, your school will continue to cover the content, give you more topical practices, and learn new content while revising what you have learned in secondary 3. In May to July, definitely there will be a mid-year exam, completion of your syllabus, and prelim revision and intensive preparation. Then around August period, you will have your prelim exams, and you will be asked to do a lot of TYS practices, 10-year series, and you have your O-level chemistry exam, right? So it's not the prelim exam, but rather the real O-level exam, the chemistry practical. Okay, and there will also be a mock O-level time trials. Of course, schools will always give this for students to prepare themselves better for the exam as well. So what can we do to actually help us to reduce our stress level and help us to strategize for the long term, okay, in a year to come? Right, so I'm very excited to announce that we have actually opened up our slot for our signature structured program to achieve our best ever result with minimum stress. Okay, so this is our limited intake every year for Sec 4 chemistry structured program. And what this structured program is basically to help you to ace your O level with ease. And what happens is that there is a classroom at Jurong East and Zoom live stream lessons that we actually have to cater to all your learning needs. Okay, so for students who want to come to the classroom, they can come to the classroom. They want to do online, they can do online as well. And what happens is that during these lessons, okay, we'll actually be helping them to revise on all the concepts that they might have forgotten and highlight the key tips and tricks for them to do better during the exam as well. Now, for us, we pride ourselves in our exceptional teaching strength. Our academic team is helmed by ex-MOE teachers as well as full-time tutors. Okay, so we have A-level programs and O-level program as well. I myself is the program head for the O-level program. Now, what sets us so different from other tuition centers is the resources that we actually provide, which is top-notch. Okay, so you realize that we actually break down your whole syllabus into different concepts that are actually bite-sized for you to learn as well. Now, you realize that our notes are not just designed for learning, and our notes are also strategically designed for you to do your revision. Okay, so during exam periods, a lot of students, right, they go and find all those summary notes, right? Okay, that are all like very concise and doesn't really have much substance in it, right? But whereas if you read our resources, you realize that we actually curated it specifically for students to actually revise as well. So there are topical guidebooks that are issued to students at a different course of study with us, and we'll be exposing them to work examples, the concepts, the typical exam questions, and concepts to stretch their learning. And these textbooks are only reserved for in-house students and are not made available anywhere else, okay? Now, there's also customized for individual learning needs. So we always place a lot of emphasis because we understand that every one of us are different. And some of us may be very, very good at organic chemistry. Some of us may be very, very good at acid bases, but some of us are also not very good at, for example, energy changes, or I'm not good at mole concept. Now, how do I do this? Okay, we recognize that every student have your own set of strength and weakness, right? So we always try and leverage on your strength to push you up, okay, to push your weaknesses up by giving you additional customized guidance for those topics and areas that you are weaker in. Okay, so you can see over here that we have our chemistry practical guidebooks, we have our Edgewise books of secrets that we always hand them to our students, okay, when we are embarking on the chapter together. So what is our four-prong approach, okay, for us to do for our lessons is the Edgewise advantage. I'm going to share with you this. Now, there's concept mastery, customized guidance, targeted curriculum, and flexible learning. So for concept mastery, okay, we explain very straight to the point. You realize that in our lessons, especially for today, you realize that we always try to enlighten you, okay, with a certain concept using a certain idea. We have customized guidance as well. Our weekly lessons are all curated by ex-MOE teachers and conducted by our full-time subject specialists using the concept-based method that has worked for many, many batches of students. Targeted curriculum, okay, we always ensure that students receive updates or as well as worksheets, and for them to actually work on their weak areas, okay, and deep result analysis when their results actually come back. We offer flexible learning for the busy student, which means that, for example, this week, I'm so busy, I cannot go for the on-site lesson. I can actually just opt for the online lessons as well. Now, the in-class experience is something that I'm actually very excited to show you. Now, during the lesson, you will actually get your hands onto the examination practice questions, structured and concise summary notes, as well as our weekly study materials, following which, okay, there'll be a 2-hour-long chemistry lessons conducted by our chemistry specialists and free personalized consultations to clear your doubts. After that, okay, you will have, after the lesson, you can have access to a support study group chat and rewatch the online lessons via our LearnEdge performance system, which I'm going to announce to you now. It is actually an all-in-one state-of-the-art learning platform, which we're going to officially launch it next year. And you can see that we have a lot of deep resources. For example, video lessons, for example, summary sheets, concise summary notes that you can watch 24/7. Okay, so what students have said about our program so far is that the tutors are always very patient and kind and using complex distilling complex examples into very bite-sized concepts to understand. And the concept learns and the notes that we provide are actually very good as well. And the lessons are very interactive, so we will make sure that we actually close up your learning gaps as well. Okay. Now, our customized learning plans are as shown. Okay, we have a regular plan and premium plan, and it is actually a very competitive, actually much cheaper than other centers outside, $70 per lesson. And if you sign up for the lessons by 20th December, we will actually free upgrade you to the premium program. Okay, and you will get access to our unlimited performance platform as well. So this is the class schedule. Okay, later if you're interested, okay, scan the QR code to actually do a pre-registration form as well to indicate your availability. So if you sign up today for our crash course sign up for classes, you will actually get yourself a lot of value. You can see how we have a 2-hour weekly tuition lesson, which is worth $380 per month. Free upgrade to the premium plan, which is $100. Okay, we have a VVIP unlimited access to our performance system, which is valued at $1,200. Same day sign up to waive the $50 registration fee. We provide exam topical guide and revision summary and priority class selection and 15% off if you decide to pay by term. Receive a $50 holiday program voucher if you sign up for 3 terms and more. So if you're interested, you can sign up today and you can enjoy the registration fee waiver. You can actually scan this QR code. If you're not very certain whether you want to sign up, you can actually submit the form as well. Okay, we'll get in touch to furnish you with more information in case you want to discuss with your parents as well. Okay, so this is the structured program. So all of these are included in the program itself. Okay, for those who are interested, you can actually sign up for this program itself. There are very limited slots. On every year, we can only intake this amount of students. We cannot intake more because we want to focus on the group of students that we actually have. Okay, all right. So if you're all good with this, can all of you, okay, if you have your phone with you, you can actually scan the QR code, okay, and fill up a short survey, okay, this QR code in the center, you can actually fill it up to actually do a short survey for our session, and you can actually get a Sherwin giveaway as well. If you have not joined our Telegram group, okay, you can join the Telegram group as well. Okay, you will actually get the free notes and study resources as well.